This video is about systems of linear equations in 3 variables, solving the systems, that is. And our method, though not an official name, I like to call this double elimination. It's a process we'll go through, and it works fairly reliably. It's just a lot to keep organized. It's really just a 3-step process. First, we're going to pick 2 pairs of equations and eliminate the same variable from each. So eliminate refers to the process of elimination, which is the method we've already discussed in solving systems of 2 equations. So same process, but now we're using that to get down to eliminating the same variable from each of these 2 pairs of equations. Alright, so we'll go through that in a second. That's step 1. Step 2 is going to be to solve the system of 2 equations from step 1. The result of step 1 will be a problem that actually looks exactly like the systems of 2 equations we've been doing, and so that should look familiar. And then thirdly, we're going to plug values back into the original equations, or one of them, to find the third variable that wouldn't have been solved in step 2. So we'll go ahead and start in with an example. The first example says to solve, and the system is given with 3 equations. The first is 2x plus 3y plus 7z equals 13. The second is 3x plus 2y minus 5z equals negative 22. And the third is 5x plus 7y minus 3z equals negative 28. Now, as a way of staying organized, which by the way is half the battle in these problems, I'm going to highly suggest that we take our original equations here and give them Roman numeral names or markings. So we really have equations 1, 2, and 3, but I'm going to mark them with the Roman numeral 1, 2, and 3 for very specific purposes. Okay, so you'll see that coming. But those are our original equations. Now step 1, as we said above, is to pick 2 pairs of these equations and eliminate the same variable from each pair. Well, to do that, and by the way, there's usually more than one way to go about it, or more than one way to pick 2 pairs. We want to pick 2 pairs that will target any variable we want to eliminate. Now, it doesn't matter which variable you pick, and so that can be both good and frustrating, because sometimes too much freedom can feel frustrating. But I like the looks of the way the z's are maybe to eliminate. I'm going to work on those simply because they already have a variety of signs, some being positive, some being negative. Really, the coefficient numbers for any of these variables aren't the greatest. There's a lot of prime number. They're all prime numbers, actually. So that means that it won't be any shortcut arithmetic-wise, but at least we have some variety in the signs, which we know we'll need for the elimination process. So I'm going to pick the z's to eliminate, and I'm going to pick 2 pairs of equations to do that with. It doesn't really matter which pairs we pick, and so I'm going to pick equations 1 and 2. Now, if I want to start with that pair, I'll look at the z terms for each, and I'd want to find a way to get those coefficients to be opposites. Notice they're already opposite signs, one positive, one negative, but I need to get them so that they're a common multiple, and most likely the least common multiple. So for 7 and 5, picking on those coefficients, I'd like to turn those into positive 35 and negative 35, being the least common multiple. Alright, so in order to pick on equations 1 and 2 and eliminate the z coefficients from them, notice they already have opposite signs, so I'm going to take equation 1, and I need to turn its z coefficient into 35. Of course, 35 is the least common multiple of 5 and 7, these 2 current coefficients. So I'll need to multiply equation 1 by a positive 5 in order to turn that into a positive 35. Of course, the entire equation gets multiplied by 5 all the way down, so that will turn it into 10x plus 15y plus 35z equals 65. Then I want to take equation 2, and notice how I'm denoting this. There's no real one way to do this, but I'm writing our Roman numeral label for the equation. I'm circling that. And then next to it, if I'm multiplying it by anything, I'm putting that factor in parentheses to indicate the multiplication. So I'm multiplying equation 2 by 7, which should do this for us. So that means I'll ultimately have a 21x plus a 14y minus a 35z equals a negative 154. Now, after that step, which it was done entirely to get these coefficients of z's to be opposites, I'll simply eliminate by adding, as we've seen in the elimination process. We're used to doing this with only two terms, two variable terms. Now we have three, but it's no different. So we're going to add down, of course, the z's will cancel. I'll have 31x, and then I'll have plus 29y, and then that's going to be equal to negative 89 when combining those constant terms on the right side. And this new equation we have now, which only has an x and a y involved, we're going to call that equation a capital A. So we're going to give it a special name, capital A. And so I'm going to label that because it's just helpful to stay organized that way. And then we're just going to hold on because we've only done part of step one. Remember that it said to pick two pairs? That was one pair, the equations 1 and 2. That was one pair. Another pair has to be picked that will also eliminate the same variable following our instructions above in the process. So let's now pick equations 1 and 3. Again, simply since they already have opposite signs, you could pick equations 2 and 3 if you'd like. You just can't repick the same pair. So if I pick equations 1 and 3 next to work on, I need to eliminate their z coefficients. Notice they're currently a positive 7 and a negative 3. We'd like to get those to be opposites. The least common multiple would be 21. So I could multiply equation 1 by 3. That would give us 6x plus 9y plus 21z equals 39. And then we can multiply equation 3 times 7 all the way across. That would give us 35x plus 49y minus 21z. There's the opposites we were going for. And then that's going to be equal to negative 196. Okay, now we're ready to eliminate by adding down vertically. This will give us, if we combine like terms all the way through, 41x plus 58y equals negative 157. Okay, now that equation, as you may guess by now, we're going to call equation B. So it's kind of like the same phase or step in the process here like we got for equation A. Now we're calling this one equation B. So notice equations A and B both only have x and y terms, no z's. That's on purpose. That's the whole point of step one. We had to eliminate the same variable from both of those pairs. Now we're into step two, which means solve the system of two equations from step one. Well, guess what? Now that's just equations A and B. So we can use elimination or substitution on them. I think we'll probably pick elimination. So let's take equation A. Looking at equations A and B, just kind of spot which variable you'd want to eliminate. They may not look pretty in either case, but you might take a brief observation and notice that the y coefficients are actually fairly related. And so let's go over that. I'm going to eliminate the y's, and to do so, I could just turn this y coefficient in equation A into a negative 58, which is actually just doubling it by negative 2, that is. So I'm going to take equation A, multiply by negative 2. That will result in a negative 62x minus a 58y equals a positive 178. And then I'm going to take equation B. Remember, our whole point is to get these y terms to eliminate, but that's already set up to happen if I just leave B as it is. So I'll just copy it down. Of course, it's 41x and then plus 58y equals negative 157. If I now just add these terms to eliminate, notice the y's are gone. That's the whole point. We end up with negative 21x equals a positive 21. That's looking good. We'll just divide by negative 21 on both sides. And that leaves us with x equals negative 1. So there we go. We actually found one of our values already. Now, in the process of solving the system of two equations, that is equations A and B, we still would have to go back and find the y variable. We could do so by taking the value of x we now have as negative 1 and plugging it back into either equation A or B. It doesn't matter which. We wouldn't want to go back to the originals yet because we have the z's to deal with there. We're not ready for that. We simply want to work our way now backwards. So it's kind of like we did phase 1 is eliminating all the way down to two equations, A and B. Phase 2 is solving those for one variable. Now we kind of want to back up one step at a time. I'm going to take this value of -1 for x, and I'm going to just go right back to equation B, which is kind of out in the open here, and plug in, instead of x, I'm going to plug in -1. And that will allow me to solve for y in that equation. And so if we go ahead and multiply through here, we'll have -41 plus 58y equals -157. And we'll want to solve that for y. Okay, so actually add 41 to both sides, divide by 58. We should end up with y equals -2 for that. I left out maybe a step or two there, but it's a simple algebra, getting y alone there. So we get -2. And then now notice we know x and y. This is the last and final step where we can go back and find z by plugging these values of x and y in for any of those equations in the original set. I'll just pick on equation 1, that is Roman numeral 1. And to plug in the values we have, of course it was 2x, but we'll call that 2 times -1. Then it was plus 3y, but now we know y is actually -2, so we plug that in for y, and then we'll say plus 7z equals 13. At this point, z is the only variable in town, so take the few algebraic steps it would take to get z alone, and you should end up with z equals 3 for that. Which means we now have all three values, x, y, and z, and so we're actually going to write our answer as an ordered triple. So we'll, in parentheses, in order, write -1, comma, -2, comma, +3 as our ordered triple solution x, y, and z. Let's try another example. This next one reads or begins as x plus 2y plus z equals 4. Let me say that again. The first equation is x plus 2y plus z equals 4. The second is 3x minus 4y plus z equals 4, and the third is 6x minus 8y plus 2z equals 8. So we're going to go through the exact same process on this one, and so as we did before, I'm going to highly recommend we continue this habit of labeling our original equations as Roman numeral 1, 2, and 3. And we got to pick a variable to eliminate from them, and kind of like we chose last time, I'm going to look at the signs of the y coefficients. Last time we picked z, right? And it doesn't actually matter. You could really pick to eliminate x, y, or z. But I like how the coefficients for the y's already have a variety of signs. It just saves us one little bit of a step by being able to utilize the opposites of those in the elimination process. So I'm going to choose to eliminate y's here. And to do so, I'll pick on, I guess, equations 1 and 2 to get started. So if I take equation 1 and look ahead at 1 and 2, I could eliminate those y coefficients simply if I double equation 1. So I'm going to take equation 1, multiply it by 2, of course the whole thing by 2. That will result in 2x plus 4y plus 2z equals 8. Then we'll take equation 2, and remember, we're thinking ahead when we're trying to eliminate y. Sometimes it's good to write that down, like maybe jot down, the variable y, that's what we're trying to eliminate here. And in that case, for equation 2, I just want to keep it as it is because those are already set up. So I want 3x minus 4y plus z equals 4. And we simply want to add down, of course, we'll get 5x. The y's eliminate, we knew that was going to happen. And then we'll have plus 3z equals 12. And as we saw in the last example, we're going to call that equation A. We've now eliminated the variable of choice. We picked y. And so that's our first pair of equation where we eliminated that variable. Now we want to go pick another pair, but eliminate the exact same variable. So again, there's not only one way to do this, but we have to just pick a pair we haven't already touched. So I'm going to pick on 1 and 3. Well, okay, we've already used equation 1, so we've already touched that one. But I'm saying you can't use the exact same pair. So we're going to go on to a different pair now. I'll pick 1 and 3. in which case I should just have to multiply equation 1 by 4, and I'll get some elimination going on with the y's there as well. We are committed now to eliminating y, since we did that in the first pair. Okay, so multiplying equation 1 by 4 will give us 4x plus 8y plus 4z equals 16. Equation 3 we're just going to drag over here because it already has the minus 8y we're going to use to eliminate the y's there. And so I'm just copying down that equation, which will end up as 6x minus 8y plus 2z equals 8. Now if we add these to eliminate, we'll end up with 10x, the y's are gone, and then plus 6z equals 24. Okay, so this now, as you can expect, we're going to call equation B. The whole point now, as you know from above, is we want to eliminate the system of equations A and B. If you take a quick glance at them, you'll notice that we might do some elimination where we take equation A and multiply it by negative 2. That would give us a negative 10x, and then minus 6z equals a negative 24. And then we're going to take equation B, but actually just copy it down as we have it, which would be positive 10x plus 6z equals 24. And you'll notice, though, if you start to add these, everything eliminates, which we weren't necessarily going for, but it's happened. So that means we have 0 on the left side equals 0 on the right side. Now, in these cases, as we've seen before with systems, when you have 0 equals 0, in other words, when the variables all disappear, but you're left with something true, doesn't always turn out to be 0 equals 0, but it's a true equation, trivially true, with no variables left. This is a case where there are infinitely many solutions. Well, kind of like we did with the systems of 2 equations recently, we're going to write our solution in set notation. So in a set of curly braces, we're going to put the generic x, comma, y, comma, z point, and then we're going to describe which kinds of those points we want by picking any of the original equations and writing it after this vertical dividing bar here. So I'm just going to pick on that first one. We'll write out as x plus 2y plus z equals 4. And that will finish out the way we can represent these infinite solutions using this set notation. There are other ways to represent these solutions, and sometimes different authors will take that route. Sometimes you'll end up with an ordered triple with maybe a variable included. There are some other ways to do that. At this level of intermediate algebra, I'm content to leave it in set notation here. Of course, this topic will be revisited in other classes like college algebra, in which case I would go further with other ways to represent the solution. But for now, we'll stop at this. Let's look at one more example. This one is, again, a system of 3 equations. The first is 3x plus 4y plus 5z equals 8. The second is x minus 2y plus 3z equals negative 6. And the third is 2x minus 4y plus 6z equals 8. We want to solve this using our double elimination process as described and demonstrated already, which means we need to pick a variable to eliminate first. And again, there's not really a wrong answer to this choice, but given the way these are set up, I would probably pick to try to eliminate the y's. Notice not only are they nice coefficients like 2 and 4, but they even have a variety of signs already. So let's go ahead and pick to eliminate the y's. And to do so, I'm going to take equation 1 and 2 to begin. Now you'll notice those coefficients are almost ready to go. I just need to double the equation 2. Oh yeah, hold on, label these originals 1, 2, and 3. And so I'm taking equation Roman numeral 1, and I'm going to copy it down. So I'll just have 3x plus 4y plus 5z equals 8, and then equation 2. But this is the one that needs some work. We're going to have to double it so it'll eliminate in these y coefficients. That'll give us, so equation 2 times 2 would give us 2x minus 4y plus 6z equals negative 12. Now, at this point, we're ready to eliminate. we've already chosen to eliminate the y's, so that should happen here. We'll just add down all these like terms to make it happen. So 3x plus 2x is 5x. The y terms eliminate as expected. And then we have plus 11z, and then that's equal to negative 4. So we'll call that equation A, kind of like we've been doing with our little naming convention here. By the way, speaking of the labeling and naming, sometimes you'll get a system where the equations aren't so nicely lined up. Like this one originally already had the x's lined up vertically, the y's, the z's, equal signs. As we've seen already with systems of two equations, there may be a need for some housekeeping to get those lined up before you dive in and actually start working on the equations. So just make sure to follow those standard like terms, stay organized, it goes a long way. All right, so we've already committed to eliminating y, and we did it with equations 1 and 2. We need to pick two pairs though, so that's one pair. Another pair could be anything we haven't already used. I'm going to pick on 1 and 3. So we'll go back to those originals, equations 1 and 3, and notice if I pick on them, the y terms are already set to eliminate. So we're just going to drag them over as they are. So equation 1 was 3x plus 4y plus 5z equals 8, and equation 3 is 2x minus 4y plus 6z equals 8, and if I add down, the y's cancel as expected, leaving us with 5x plus 11z equals 16. And again, we'll call that equation B, just keeping with our naming convention here. Okay, as you know from above, in these steps and the example we've already done, our next step is to do elimination with equations A and B. That's again why this is, or why I call this double elimination. We've already done some elimination, but now we do it again, but with a different set of equations. So if I take equations A and B and just glance at them for a second, you might notice some striking similarities. If I were to simply look and say, you know what, I'd like to eliminate the x terms from A and B, notice they already match exactly, which means I could eliminate them by taking either equation, I'll pick on A, and multiplying it by negative 1. That would give us a negative 5x minus 11z equals a positive 4. If I just take equation B as it is and drag it down, I'll have 5x plus 11z equals 16. And with elimination, I'm set to add vertically with like terms. Notice the x's eliminate. That's kind of what we were expecting there. But notice, so do the z's. That means we have 0 on the left side. On the right side, though, we have 4 plus 16, which would be 20. But, okay, when the variables all disappear and what you're left with is not true, such as 0 equals 20, that means, as we've seen before, that this is a case of no solution. So we put a 0 with a slash through it. And even in the case of a system of 3 equations, as soon as we hit this scenario of a non-true equation with no variables left, we can stop and say no solution. There's no need to go any further with it. So that's kind of nice. Beyond this, now that you've seen examples of solving these algebraically, it's typical that a textbook may have maybe some word problems associated with a section like this. So they may give you a word problem or two that involves translating from language to the system algebraically and then solving it. This video topic is just showing you the methods of solving the system of 3 equations. Typically translating from a word problem into a system of 3 equations like this may be more likely for a class that might follow this one, such as college algebra, but there could be examples in the case of intermediate algebra, in which case use the same translation methods and skills we've learned from doing it in previous topics, such as solving systems of 2 equations, and then use this video's topic of double elimination to actually solve it algebraically, and then of course translate it back into a solution that makes sense. Additionally, in a topic like this, it's possible that a textbook may address this topic with a matrix or using matrices, and that is a very valid way to address a system of 3 equations like this, but this was simply done by hand, and that's our scope for now. Certainly in a college algebra course, that topic I would definitely address with matrices as well as by hand. This is simply doing it all algebraically by hand.